Okay, good morning, everyone. I guess we can get started. So, my name is Tjerand Silde. I'm working at Poland Biometrics. And this morning, I'm going to talk about cryptographic side channels on embedded devices. So first, a few words. I'm working as a security and cryptography expert at Poland Biometrics. We're a company or a startup here in Oslo, working on biometric authentication and FIDO. And specifically, we're working on how to implement cryptography in embedded devices, such as the off-pad that I showed on the first page. And this is kind of a product to allow for secure authentication without passwords. And then we're using cryptography. And there's a lot of challenges that shows up when we're implementing cryptography on embedded devices. So that will be the main topic of this talk. Otherwise, I'm also working as a associate professor at NTNU in Trondheim, mainly focusing on quantum-safe cryptography and privacy. And I'll mention a bit about the former at the end of the talk. I'm teaching a course there on secure cryptographic implementations. So this is also kind of covering this topic more in depth. And we have roughly 50 master students this year actually taking this course and specializing in this topic. And otherwise supervising master thesis and PhD projects on cryptography in general. So the outline of this talk will be as following. So I'll talk briefly about what kind of cryptography we're using today. But the main focus of the talk will be discussing this difference between this black box approach to cryptography, where you have algorithms or protocols doing something for you, and the leakage that you might be able to observe when you do this in practice and when it's implemented on, for example, an embedded device. We'll look at side channel attacks. So what are these kind of attacks? How can these be used to attack cryptography? And finally, also how we can mitigate these attacks and protect our implementations. And finally, a bit about quantum-safe crypto, because I'm mainly going to talk about algorithms that we know to use today, like AES or RSA or Diffie-Hellman. But we are soon about to change everything we have of public key cryptography into quantum-safe cryptography. And then we will meet some of the same challenges there in the coming years. So let's dive in. So if we're looking at what kind of cryptography we use today, it is quite a broad field, but there's mainly three kind of underlying primitives that is being used. One is public key encryption. I guess you are all somewhat familiar, but just to recap. Here we have a public key. This is available to everyone in the world. And anyone can take a clear text, use the public key to encrypt it, and you obtain a ciphertext that you can send over an insecure channel. This ciphertext is then public, but only the person with the secret key can decrypt and get the clear text back. Furthermore, we have digital signatures. You might want to sign a message or some software of arbitrary size. You usually hash it down to a bit string of 256 bits, and then you use the private key to sign it. You publish the signature, and everyone with the public key can verify that the signature is valid. So this is the two categories that we have of asymmetric cryptography. And they're kind of opposite in the way that in encryption, the public key is used to encrypt, and only the person with the secret key can decrypt. While for digital signatures, the signing key is secret, and only the person with the signing key can sign, but anyone in the world can verify that the signature was correct. Then we also have symmetric key cryptography. Here you have, again, some message or clear text that you want to encrypt, and you're using your symmetric key to encrypt it to get a ciphertext. But in this setting, you also need the symmetric key, the same one, to be able to decrypt in the end. So this key needs to be shared in advance between the sender and the receiver in some way. And the way we implement this in practice is usually a combination of the two. So you might be familiar with using Diffie-Hellman for key exchange, and then using AES or some other symmetric key cipher to actually encrypt the message you want to send. So in this example, if we're looking at Alice, you have a private key A. This is some number that is secret to Alice. You have a public element alpha in this case, and a public prime P. These green values are public. And then you generate the public key by combining this public alpha base element with your secret exponent A. Then you can exchange this value. You get the B value from Bob, which is computed in the same way. And the shared key is a combination of your own private key and the public key of the person you're talking to. So the main point here is you do some algebraic computation to be able to achieve a shared key that only Alice and Bob knows. And then you're using this to encrypt the message. So you're using the key K to encrypt the message. You get some ciphertext or garbled mess, which you can publish and share. And then the person on the other side can generate the shared key in a similar way using their secret key combined with Alice's public key. And then you're using some algorithm like AES to then decrypt the message. So often you need to handle several primitives, in this case both Diffie-Hellman and AES, and you need to handle several keys and several algorithms. And all of these things matter when you then want to implement this in practice to make sure that this is done securely. So this is, for example, how it's done in TLS, but also most other protocols where you want your devices to communicate. But for now, we just looked at this at the high level. This is some mathematics on a screen. You know, how do you implement this in practice? And this is where the challenges come up. So let's look at what we mean by challenges and side channel attack. So then we need to discuss black box cryptography and leakage models. So in general, when we design a new cryptographic scheme, the principle is quite old, coming from Kirchhoff's, saying if everything about the scheme, except for the key, is public, the scheme should be secure. The key is the only thing that should be secure. Of course, you probably heard about older schemes like, you know, the Caesar cipher, where you might just replace all of the letters in the alphabet with some shift. Or you might be familiar with the Enigma machine. And then part of the secret was also how you encrypted messages. Okay, so for example, with the Enigma machine, they tried to keep the machine secret and hidden so that no one could analyze how things were encrypted, in addition to having the key being secret. But nowadays, everyone is using the same algorithms. AES is a standard that is being used for all symmetric key encryption, essentially, worldwide, no matter which country you're from, what kind of application you're using, and so forth. This is a public algorithm, and everyone knows how it works and everything about it. And the only thing that should guarantee security is that the specific key used to encrypt a specific message is secret. And when we study these algorithms, at least from a cryptographic perspective, we often look at them as black box, where there comes some input into the function. It provides some output that is of a specific form. And we want to prove security by showing that based on this view of the adversary, they cannot break the scheme. There's different ways of doing this. For example, with RSA encryption, you want to say that if factoring is hard, then the scheme is secure. So you're looking at the input and the output and the communication, and you want to say that, well, you cannot break this unless you can break factoring. But then the view is quite simplistic. So you have some encryption algorithm, E, which is known. Everyone knows how it works, at least have a mathematical description of it. You have a decryption algorithm. Everyone knows also how this works. You have some adversary, let's call her Eve, which is looking at the communication between the two parties, Alice and Bob, and can watch whatever they're sending to each other. And they know, at least mathematically or algebraically, how this was computed. Right? So if you see RSA ciphertext, you know that this is some message to some exponent, which is known, to some modulo, some public integer. Okay, so you know all of the parameters for the encryption and everything, you just don't know the key being used to decrypt. However, when we want to use this in practice, there's a lot of other things that matters. For example, how these algorithms to compute, for example, the exponentiation in RSA, how is it implemented in practice? And what kind of information leaks from the device when it's running? And how does this depend on the secret key being used? Okay, so this also matters. And then you suddenly have a much more complex picture of the setting you're in and the information that you provide to the adversary. So this is a way to, like when we model security, we often look at what kind of powers do the adversary have. And we want to be secure against the most powerful adversary we can think of. So we have to give them as much abilities as possible, and still we want to have a secure scheme. So then not only the mathematics matter anymore. Of course, if you don't have that, you have no security whatsoever. Okay, but it's not enough. And even it's not enough that the algorithm produce correct outputs, right? Because actually additional information leaks even if the algorithm is correct. So if we're looking at this photo now, there's a lot more information available to the adversary, like the electromagnetic radiation. Maybe you can measure the heat or some sound being made by the device when it's computing. You can measure the power consumption. You can measure the execution time. Maybe you can inject faults so that it impacts the correctness of the algorithm, and this also leaks information. Maybe you get error messages that helps you learn something about the key based on what went wrong, and so forth. So now we're trying to paint a more realistic photo of what information do the adversary get. And then it's important that we can protect against these things. So to summarize it, the leakage is actually, quite devastating in practice, and maybe more on embedded devices than others. And this is because often the CPU is more exposed. Often you run fewer processes simultaneously, which means that you get more pure data source when you want to analyze the leakage, because there's not much, other things going on at the same time that might pollute the analysis. And also the classical example is that some embedded devices actually get their resources from the environment. And a classical example here is if you have a credit card, there is a secure element on the credit card, and this computes digital signatures when you want to approve a transaction. But the credit card itself doesn't have battery. It actually gets the power from the terminal that you're using for the payment. So the terminal actually knows exactly how much power you're using and in any point in time. And this might be very valuable information when you want to analyze or try to even attack the signature key. Okay, so we need to prevent this. And just to give you a very small example, this is very simplified, but the idea here is the same as when we start looking at the more advanced cryptographic schemes. In this setting, you want to check if some password is correct for a user to authenticate themselves. So you have some password stored, and you have some user input. And then to check if it's correct, you first check if the length is the same. If it's not, obviously the password has to be wrong. So then you decline the request. And next, if they have the same length, then you check character by character to see if they match. If in any point in time they're not the same, the password is wrong, and you output false. Okay, and only at the end, if everything goes through, then you acknowledge the password to be correct and you let the user in. And this was how things used to be. Okay, and I guess you can already think of a few ideas of how this is not secure. So if you measure, for example, the time it takes for the machine to tell you if the password is correct or not, this might leak information. So if you get a really quick answer saying denied, then most likely the length of the password is incorrect. So then you can just try different passwords until it takes a bit more time. And then you know that, okay, now I know the length of the password. I have some information about the secret. And then you want to check, well, are the character correct or not? And then you can again guess. So you can try all A's, for example, and see how long time does it take before you get the wrong answer, or like you get denied. And whenever it takes a bit longer time, your guess was correct. And then you do this letter by letter. Of course, here we're assuming that you can try many passwords, and ideally today you have some kind of rate limiting for this. But if you think of cryptographic algorithms, often you can connect to a server that allow you to, do handshakes as many times as you want, and they're basically doing, the same operation every time based on the same key, and you can either measure how much time it takes, maybe even how much power it uses, and so forth. So this is kind of same idea that applies to if you want to attack RSA or Diffie-Hellman or AES in practice. Often you have almost unlimited number of queries you can ask, and you can learn some information about secret passwords or keys in each of these queries. So this is something that we obviously need to protect against. So if we look then at side channel attacks, the idea here is that we exploit leakage in the implementation of a scheme, and the goal is to extract keys. Okay, so now in the black box setting, this is information you didn't have. Okay, you only had like the output, and you know how algebraically it was computed. But now you get additional information that you can combine with the information that you obtain through watching the channel. And while combining those, that might give you extra information and allow you to break the scheme. And in general, we use then different kind of statistical methods to analyze this kind of leakage from one or more traces. And again, to showcase how this might be useful, say that you have some algorithm and you have a key which is a bit string. Okay, and this applies to most kind of schemes. You can represent it as a bit string, or that the computation depends on the bit representation of your key. So in this case, by looking at the power consumption, only one trace, you can essentially say something about the key if you know how the algorithm is implemented. So for example, if you have a key and you have an algorithm that do something if the bit is 0 and it does something else if it's 1, doesn't really matter what it does in each case as long as it's different. That's the only thing that matters. If it does something on 0 which takes less power than the other computation that you do if the bit is 1, then you can measure the power consumption while the device is computing this algorithm, and then you can basically read off the key just by looking at the graph. So in this setting, you see that whenever there's lower power consumption, then it's a 0. Whenever there is a spike, that's a 1. Then you can just read off the key from one power trace. So this is really serious, and we need ways to mitigate this. We also have different kinds of attack. So we usually classify them in a few different categories. again, to fit our adversarial model. Okay, so what do we allow the adversary to do? Or, what's the realistic context of an adversary against our specific algorithm or product? Okay, and this might vary, but some of them are very generic and basically apply to all kind of situations, and other ones are more specific, and you might need to work a bit harder to protect your code. So one way to classify them are remote versus physical attacks. Can you do this from a different location, or do you need to be in proximity of the device itself? For example, if you measure timings, this is something that you might be able to do over a network. You can connect to some server, you get replies, and you can measure the time. And if you know how things works, and maybe you know something about the latency that you can factor out, this gives you a quite accurate picture of how much time is spent for doing specific, say, cryptographic operations. Power consumption, on the other hand, often require you to be somewhat near the device and be able to measure something physically. We also have passive versus active attacks. So passive in this setting means you're just listening. Okay, you're just observing. Okay, but while active attacks might include that you are interacting with the device, or maybe you're measuring something on the device physically, maybe you have access to the same hardware, either shared resources, or that you have the device physically in your hand and you can measure things. So again, measuring, timings or the power consumption, this is passive. But if you want to do specific, inputs, or if you want to do a lot of requests, or be able to force things to happen, then you might be more active. And finally, you also have invasive versus non-invasive attacks. So an example of a non-invasive attack would be timing attacks, for example, where you're just, listening or waiting or something like this. You're not really doing much with the device itself. You have semi-invasive attacks where you might, connect a probe or something to the device, but it doesn't really impact the device itself. And then you have more invasive attacks where you might want to physically try to open up the device, or inject faults in some way by connecting it to some kind of external source of electromagnetism, or pointing a laser at it, or like even physically try to scrape off layers of protection or something like this. Maybe even damage or destroy the device itself. Again, it really matters like what kind of power or capabilities do you give to your adversary. So from this, it seems quite natural that at least you need to be able to protect against remote, passive, non-invasive attacks. This is something that is low effort, that someone can do from wherever, and it's like the minimum you need to protect against. And then based on your threat model, you might decide to do more than this. So let's look at one example, AES. So that's an algorithm that you use for symmetric key encryption. So you have some key as input and some plain text. And the algorithm works basically as this. It has 4 subroutines. One is add round key, which is basically an XOR with a key for a different round of the algorithm. And then it runs for X number of rounds, where you do the subroutines, substitute some bytes, you shift some rows, you mix some columns, and you add another key. And finally, like the same procedure basically at the end. Okay, so it doesn't matter too much right now how these different algorithms work, or the subroutines work, but this is like the structure of the algorithm when you want to encrypt some information. And just by looking at this and imagining, if you measure the power consumption while this algorithm is running, you can already learn some kind of information just by looking at power traces. Okay, some of them are not really secret, but let's mention them anyways, just to kind of set our mind on what kind of information might leak. So for example, we can easily see from the power trace how many rounds are computed. We can see exactly what kind of operation or subroutine is being called at any point in time. And we can compare traces. So for example, if I can control the plain text message, so we go back to the previous slide for a second, the key is fixed and secret, but the plain text is coming from somewhere. So for example, if I have an active attack where I can choose the plain text, I can adaptively give you different kind of plain text messages to encrypt and try to measure the power consumption. And then I can try to see how does the power consumption change when you apply the key and the different algorithms based on, for example, the Hamming weight of the plain text message that I chose. Does this impact the power consumption, and how does it correlate with the key that I added to it? Okay, maybe I can do many requests for encryption, and then I can look at the differences between these power traces and learn some information about the key being used just by doing this. Okay, so I can start, for example, with the first round, then I can learn some bits about the key being used in the first round of the scheme. Maybe after many traces, I can learn some bits and maybe even the whole round key. Okay, just because I can choose the plain text, I can look at the power consumption, and I can compare the traces across many different plain text messages. I can choose them with the Hamming weight I want. I can choose exactly if it has many bits set in the first part or the last part of the message and so forth. So if we look at more potential leakage based on the different underlying subroutines, again, not going into detail about the subroutines, happy to discuss those with you after the talk if you're interested in more details. But for example, the add round key computation might leak the Hamming weight of the key, because you can look at how much does the processor work to do this operation. And if you know the Hamming weight of the input message, then this might tell you something about the key. The sub-byte algorithm, this is a non-linear operation. In practice, you're computing some inverses, or you're doing a division operation as a part of the subroutine. Doing computing inverses and in general doing non-linear operations really depends on the value that you're trying to invert. And if you can pre-compute and measure how much power it takes to invert any element in this algorithm, maybe the power trace itself is enough to identify which element was inverted here. Right? So again, if you know the plain text, you know that there is some unknown key added to it, but you know exactly which element was inverted, you essentially know the key as well. So this might leak information. You have mixed columns, which is essentially a polynomial multiplication. Again, how you perform this multiplication also might depend exactly on which elements are being multiplied. And if you again pre-compute all possible multiplications for this part of the algorithm, you can look at the trace and you can recognize which element was multiplied here, and suddenly you have extra information about, the inner workings of the algorithm, which again depends on the secret key. And all of these operations are algebraic in some sense. They're working over a field, basically saying that you're taking a byte and you can do multiplications, additions, divisions, and so forth with each byte. And how these algebraic operations are implemented might, leak information about which element is being computed on at any point in time. Okay, you basically have a fingerprint of each element that you can look for in the power trace, and you can recognize them, and you can say, okay, this element here was used in this part of the algorithm, and then you can analyze how does it depend on a key, because the algorithm is public, right? In most cases, not even the algorithm is public, but also the code being used is public, right? we don't have that many cryptographic libraries available. OpenSSL and others, or Boring SSL and so forth, are being used by a lot of people. And often this is not secret. So if you know which library they're using, you know exactly how the implementation works. And then you can rerun all of these tests on your own device and do these checks. So this is just information we need to assume that the adversary have, and capabilities that they might have, and information that they have available when they want to try to attack your scheme. Moving on. So for public key cryptography, both in Diffie-Hellman and RSA, also in the elliptic curve variants of Diffie-Hellman, we need to compute modular exponentiations. Okay, this is the key, or this is the crucial operation that you do based on the secret key involved in the scheme. And because this is the secret key, then we need to protect it against high channel attacks. So if we're again looking at a very naive way to implement this, but if you look at any textbook, this is how they introduce it, right? So if you actually implement what's in a textbook, you're doing it in an insecure way. It is correct, but it's insecure. Okay, there's a difference. So here you want to compute some exponentiation. You have some, well, in this case, maybe a decryption. So you want to compute a message, you are given a ciphertext, and you have a secret key D, and there is a public modulus N. And basically what's happening here is that you look at the bit representation of your key, and then for every bit, you do a multiplication, and you do a squaring, so you multiply the element by itself. That you do for every bit, and if the bit is 1, then you also do a multiplication. So the name of this algorithm is square and multiply, and you see that the running time of this algorithm is basically log D. Okay, which is exponentially much faster than just computing it directly or trying to find the exponent D as an attacker. Okay, so this algorithm runs in log D time, and you basically do log D squarings, and you do maybe 0.5 log D multiplication, because roughly you have half and half zeros and ones in a randomly generated key. And looking at this algorithm, maybe you recognize this from the graph earlier. This is basically an algorithm that do something if the bit is 0, and it does something else if the bit is 1. And you do more work if the bit is 1. So you can basically look at the power consumption and see if there's low amount of work, it's a 0. If it's high amount of work, it's a 1. And one single power trace is enough to break the whole scheme and learn the key. Okay, but this is how it traditionally were implemented before we learned about side channel attacks and what we could do with those. And this is how it's presented in textbooks, usually to show two things. One, how to do it efficiently, and secondly, just to look at how can we do scalar multiplications in a kind of simple way with modular arithmetic. Of course, the modular operation and the multiplication operator here, like this is Python, or you can think of it as pseudocode. So this might be underlying subroutines doing these operations. So this also matters if those subroutines take varying amount of time or power consumption based on the input. So there's both say binary operations, and it's the algorithm that both might leak information about the key being used to compute the result. So what if we do some simple trick to this? The only thing I did was to add an else on the bottom, which is basically a dummy operation. Okay, so now I make sure that independent of the bit being 0 or 1, I do roughly the same amount of work. Okay, and this is one step towards, how do we protect against these things? just to make sure that the running time or the power consumption of the execution of the algorithm is independent of the key itself. Okay, so this might be one way to do it, but it's not really a good way, and there might be ways that this goes wrong. For example, the dummy operation might leak memory information, and because you're computing on a different variable, this might actually be measurable by an adversary looking at the computation. Right? Did you access the same memory allocation as earlier, or did you access a new one? Okay, maybe the stored value and the Hamming weight of that might impact, again, the trace. So instead of getting this 0 trace and the 1 trace, you might get a dummy trace as well. Okay, and then we're back to square one. If you have a really smart compiler, they might notice that it's a dummy operation. You're never going to use X again later. It just ignores it when it compiles the program, and you're back to what we had. There might be also another kind of attack where you inject faults. So if you have really like a good precision in your attack, you might be able to point a laser at it and shoot at the right time. This might impact the computation. And if you do it exactly when this if the computation is being done, and you know if it was the 1 path or the 0 path, and you inject the fault so that you get impact the result, and you get the wrong result in the end, you can see I injected one fault. Did the result come out correct or wrong? If it was wrong, I know that I did impact the computation that depended on the key. If it's still correct, even though I injected a fault, you know that you hit the dummy operation. So again, if you do this one time per bit, that's enough, again, to read off the whole bit string, and you have the secret key. So introducing dummy operations, might not help you as much as you wanted to. So we have a third variant, and this is basically what's used in practice, at least some version of this. And here you do the same computation even if the bit is 0 or if it's 1. You do 2 multiplications in both settings, and you compute on all variables, so you can't inject faults and look if the result is correct or not, because in this setting, if you inject the fault, it will always give you the wrong answer in the end. Okay, so all steps of the algorithm depends on the secret key, but they all are also regular in the sense that you do the same thing independent if the bit is 1 or if it is 0. You always do it. Okay, and you might even get rid of this if test by having some kind of logic statement. That way you end up computing everything and you all sum together things, and then you have a coefficient 1 or 0 in front of them to just say if they impact the result or not. But this algorithm is called Montgomery ladder, and this is probably what you will see in most libraries nowadays if you're looking at code implementing either RSA or Diffie-Hellman or DSA or something like this. Whenever you're doing modular exponentiation, there will be some algorithm like this below. So here we see that, again, we make the algorithm regular, and the output depends on everything we do along the way. Even if this is much better, it might not always be good enough. Okay, so for example, if you're given many traces depending on the same key, and we can adaptively choose the ciphertext you should decrypt, for example, in a previous example, often you can choose this input. You might still leak information across, millions and millions of power traces, for example. So we can do, a bit better, but this at least takes care of this general problem. It protects against timing attacks, it protects against remote attacks, and so forth. So this seems to be like the minimum and what you should expect from any library today. And maybe there's more countermeasures. So let's look a bit general on what can we do based on what we have seen so far. So some standard approaches are the following. We want the code to be constant time, basically independent of the secret being used. Okay, so how many ones and zeros you have in your bit string should not impact the resources used to compute the algorithm. You might add some randomization to it by introducing randomness in some way. We'll discuss 2 different examples in a second. You can split up the key and do partial operations based on a random splitting, so that this is kind of unique and random and different every time. You should definitely check that the outputs and inputs are correct and valid, that they fit the parameters of the scheme, for example, that the points are on the elliptic curve that you're using and so forth, and that the computation was correct. Okay, maybe by redoing it or having some checks that you can use to tell if things went well or not before you output. And you could add noise to the computation, for example, delays that would impact timing attacks, for example. So these are kind of general strategies that we try to use in different ways based on the algorithm that we're trying to protect. So for example, for AES, a common term is d-order masking. It basically means you take your key, which is a bit string, and split it into d parts. And the way you do it is you sample d-1 random bit strings, and then you XOR them all together as well as with the key to get the last share, so that all of these d shares XOR together to your key. And then you compute the algorithm on each of these random key shares. And linear operations, right? If we're doing additions or scalar multiplications, we can do this in parallel. Okay? We cannot do multiplications of secret elements in parallel. Then we need to do some extra tricks. So this means, for example, that add key, this is just XOR operation. It's linear. We can do it on each key share. Similar with shifting rows and mixing columns. These are all linear operations, and we can apply them to each of the d key shares independently of each other. Subbytes, it's not linear. This is the inversion I mentioned earlier. So here you're basically doing a multiplication by a specific element based on your input. This requires some extra work, but that's kind of the cost, basically, of protecting the implementation. And when we're looking at different attacks, the analysis that you have to do, the extra effort that the adversary have to do is exponential in d. So for example, if you have 5 shares, d is 5, the adversary need to do 2 to the 5 times as much work as earlier to analyze the, for example, the power consumption during the operation. Because then you need the traces of all d shares instead of just one, and you need to be able to analyze them, for each trace. But each trace is independent because you split your key into d random shares every time you encrypt something. You don't split it into d shares and reuse it. You just do it once, and then you do it freshly for every time you do it. So this is basically the state of the art today to protect schemes that directly imply or use bit strings and binary and byte operations as a part of the algorithm. The added work is basically that you do d log d much more work than you did earlier. It does have a cost in running time and power consumption, but it gives you exponentially more security based on d against an adversary measuring power consumption, for example. Okay, so this is the trade-off. For public key cryptography, basically everything is some kind of modular arithmetic, so we can use algebraic countermeasures. So for example, we need to look at how we do the modular operations like multiplication and reduction, mod n. They need to be constant. We need to use regular algorithms like Montgomery, where we basically have a constant time algorithm where the running time doesn't depend on the specific bits of the secret key. We can randomize base elements and exponents. So for example, in RSA, for those of you who know the details, you have some order that you're working with, which is p minus 1 times q minus 1. This is the order that you're working through when you generate your keys. Your keys E and D, they multiply to 1 in an exponent. That's why you get correctness when you decrypt. So if you add a small multiplum of the order to your keys, that disappears because that gives you another 1 in the exponent. So you can add this to randomized operation. You can also randomize the input. So for example, maybe let's go back so that you can have a look at it. When I get C in, I know that C was computed as some message to the power E, which is the public key. If I sample a random number R, I take R to the power E, and I multiply this with C, then I have a new valid ciphertext of M times R. So then I can do the whole decryption procedure. What I get back is M times R, but I know R, so I can divide by R in the end. So then I have basically computed this on a random element C instead of the C that I got from whoever invoked the algorithm. And I can sample a fresh random value every time I want to compute this algorithm, so that even if I use the same key D, the element I'm computing on is uniformly random every time. So I mask it before I start my procedure and unmask it after my procedure is done. And then the computation is independent of the input that I got. Again, and specifically when it comes to public key cryptography, we need to ensure that inputs and outputs are valid. There is quite dramatic attacks against elliptic curves, for example, if you're giving points that is not on the right curve. So you really need to make sure that these are valid inputs, and check that the outputs are valid as well to make sure that it doesn't leak information in case that someone injected a fault. Okay, so these are the general ways that we go about protecting these implementations. So we have some minutes left, so let's end the talk by looking a bit at quantum safe cryptography. This is something that most of you will probably face in the coming years. So there's been a lot of development recently about building quantum computers, and they're getting more and more powerful each year, and this poses a threat. So for example, if we look again on the algorithms that we use today, in general, we're using RSA for encryption and signatures. We use Diffie-Hellman for key exchange. We use digital signatures, and sometimes even El-Gamal encryption, either over prime fields or elliptic curves. This is the most common algorithms for public key cryptography. And for symmetric key, we're using AES or similar block ciphers for encryption, hash functions like SHA-2 and 3 for integrity checks, and MACs like HMAC. So these are some of the common primitives that we see. So how are they impacted? Well, we have two quantum algorithms that we care about. One is Shor's algorithm, and one is Grover's algorithm, and both of them were published in the 90s. Of course, we don't have, as far as we know, powerful quantum computers available today. So it's really hard to implement them and test and see how they actually work. Okay? But in theory, they are very efficient. Okay? The running time in theory, based on what we know about quantum computing, makes them efficient. And Shor's algorithm efficiently finds the periodicity of a function. And this problem is very related to both factoring and computing discrete log. So basically, Shor's algorithm applies to all schemes that we use today within public key cryptography. Grover's algorithm, on the other hand, can be used to speed up search, to find something in a haystack, basically, right? And this can be used to speed up algorithms trying to find symmetric keys or to find collisions in hash functions. Those are basically search problems. So if we look at the impact, this basically means that all of public key cryptography that we use today is dead. This is insecure. At least in theory, these algorithms break the schemes as fast as it takes us to use them. Okay, there is no asymmetry in using the schemes and breaking the schemes. While for symmetric schemes, the impact is less. So here it's still kind of an ongoing debate if Grover has any effect in practice, because it's quite complicated to use it in designing attacks against these schemes. Best case, we don't have to do anything, and that's usually the stand that different kind of national agencies are taking nowadays. You don't need to do anything. Worst case, you need to double the key length. Okay, so the attack basically gives you a square root advantage, which means the bit security is half, which means if you double the key length, you have the same security as today against classical computers. If we're looking at AES, where usually we use AES 128 today, but AES 256 is already standardized, sometimes used already. So we already have a fix ready and available. Same thing with SHA-2 and 3. Usually we use the outputs nowadays with 256 bits. We already have standards for 512 bits. This is already available. If we are afraid of this attack, we can just switch to something else that is already standardized, if we want to. Okay, so best case, we don't need to do anything. Worst case, we just use something else which we already have available. Okay, but for public key cryptography, everything is dead. So I just want to give you a quick primer on what does post-quantum cryptography look like. We have a few standards which is published already, and they're essentially relying on this problem. This problem is called learning with errors, or LWE, and it works as follows. You have some public matrix A, the blue one. This is information that you share to everyone. You have two vectors that are secret. This is your secret key, the orange and the yellow one. And these are vectors where all of the coefficients, or the elements in the vector, have small values, or small norm, if you want. Okay, so you have some modulus Q that you're working over. You're sampling this A matrix, the blue one, uniformly random over Q. But the orange and the yellow, often called S and E for secret and error, they are small, for example, binary or ternary, okay, or very small compared to Q. Then you compute this linear product. You output the brown vector, often called B, and A and B, the blue and the brown, that's your public key. And the orange and the yellow is your secret key. And the hard problem here, equivalent to factoring in RSA, is that given A and B, the blue and the brown, you cannot tell if the brown one is sampled uniformly at random, or if it's computed like this based on a short orange and yellow vector. That's the new hard problem that seems hard even for quantum computers. So post-quantum cryptography is cryptography that we can use on classical machines, you know, your laptop, your embedded device, your phone, whatever, and relies on this problem instead of factoring and discrete log, and then we can build encryption and signatures based on this. And the main operations are linear operations mod Q. And there are two standards. One is called ML-Chem. This is for encryption. So this will replace Diffie-Hellman and RSA. And we have a signature scheme called ML-DSA. Both of them are based on lattices. This is FIPS 203 and 204. There's also coming more, but these are the general purpose key exchange and signature schemes that will be used going forward. And they're both based on this learning with errors problem that I showed you. So these will come and be required soon. So some of the challenges we then face is, one is performance. Signatures in ciphertext and public keys are in general larger. You need more memory to compute things. Sometimes they're faster, sometimes they're slower. It depends a bit on what you're comparing to and which device you're running it on. There's new foundations. So this learning with errors assumption is new to most people, even though cryptographers have studied it since basically year 2000. New models for cryptanalysis based on quantum computers and so forth. So there's still kind of a lot of research and development going on here. Side channels was not something very important during the standardization process. And actually several of the algorithms that we have standardized are difficult to protect against side channel attacks. So this is really something that we need to find out how to do. We do have, a lot of experience from protecting symmetric key and public key with the primitives we are using today. So I think a lot of that knowledge also goes into these new algorithms. But they are different, and we need to think about different things. And there is every week now, like new papers about analyzing and protecting these kind of algorithms, both the standards and ongoing standardization candidates. There's also a lot of different use cases. Sometimes you want to combine what we have today with post-quantum so that you get some kind of hybrid solutions. You have different standards in different countries and regions. So the US and NIST have standardized some algorithms. BSI in Germany have standardized other algorithms and so forth. So there's kind of a zoo of algorithms out there, and we need to make sure all of them are correct and compatible and so forth. So there's some challenges going forward, and this is basically where we are today, and see, how do we integrate them in larger protocols, and how do we implement them securely, and particularly on constrained devices. I'm at the end, so I want to say just the main takeaways from this talk is that when it comes to cryptography, correctness is not enough. You also need to care about how things are implemented to protect against leakage in the implementation that depends on the key. You should be aware of side channel attacks and what to look for. Most of you will probably not implement this yourself, but you are often finding some library that you need for your application, and this is something you should ensure that this library offers. There exist many techniques, and I talked about some of them, and they're different based on the scheme that you want to protect. And we face a lot of challenges now that we have to do the same thing that we have done for 20 years with RSA and Diffie-Hellman and AES, now apply to the new standards ML-Chem and ML-DSA and more. If you think this is interesting, there's a nice book that I can recommend called The Hardware Hacking Handbook, which is about embedded devices and attacks and protection mechanisms. And if you want to buy equipment and do these kind of things yourself, I can recommend looking up Chip Whisper Husky. This is equipment dedicated to do side channel attacks and which helps you doing these kind of measurements so that you don't need a very expensive and difficult lab equipment to use. This is much more available. Cost everything from a few hundred kroner to a few thousand, depending on how much you want to do. And this is also what we're using in my course at NTNU, and that students are running experiments on as we speak. And by that, I'm at the end, and thank you so much for listening, and I'm happy to take questions either now or after the talk. Thank you. Yes.
About AI. AI very good at finding patterns and shortcuts and everything.
Mm-hmm.
Do we see new threats with these kind of tools?
So in some sense, you can say AI is some statistical tool, and this is what we're using already. We have seen some papers recently using AI and training them on power traces to speed up this analysis. So that's more like in the evaluation of the traces that you get where this might help you. It doesn't seem to dramatically change what we can do, but it might, speed up certain things. Yeah. Yes.
There are people that basically say, okay, because of the issues, we should hide our implementation with libraries, we use and all of these. What is your take on that? What do you think?
My take on that we should hide the code is that in general this leads to vulnerabilities because it's so much you need to think about, and whenever we see things being re-engineered or open sourced much later, we often find a lot of bugs. So I don't think that's the best approach. I think being open and transparent and using open source tools and pay experts to analyze code and so forth is the best way to go forward. I'm over time, so I think I'll end here, but I'll stay around if you have something else you want to talk about. And so, yeah, thank you again.